Okay, the topic area for tonight is pre-processing. So this is more of just getting the data ready, but more advanced things that you can do with the data outside of just TensorFlow. I mean, TensorFlow itself is relatively straightforward. You get the X, you get the Y, you pass it in, and you either classify or regress. And I think there's been um, some confusion on that from some of the questions I got as far as classification and regression. It's definitely I'll review that a little bit when I go into the program assignment, but there's a different neural network function that you use for classification versus regression. So it's very important that you use the correct one, or you'll get a variety of errors. But the material for tonight is pre-processing. This is where I spend a vast majority of my time with data science. Is we get data in, but to put the data into TensorFlow or just about any machine learning model, you have to reformat it and twist it so that it fits into that nice feature vector with all the consistent columns to go into there. This is one of the real advantages of deep learning when we get into the LSTMs, which we'll look at in a couple of weeks. You can get away from that very rigid sort of fixed length input, and we'll see how to do that. It's very useful for time series, so predicting things that are happening sort of over time and in time. Scikit-learn, which we've been using jointly with TensorFlow, has a whole lot of stuff for pre-processing. If you go to that particular page, you will see all kinds of stuff here. A lot of packages on freeware packages for Python and other programming languages. Sometimes the documentation is not particularly good. Scikit-learn actually has extremely good documentation for some reason. That team really makes that a priority. You can learn a lot about machine learning just by reading the Scikit-learn documentation. This originally started out as a Google Summer of Code project and has just pretty much gotten a life of its own. TensorFlow, at least in my opinion, doesn't have as good of documentation. It's also a lot newer than Scikit-learn, so that's what I spend a lot of time between classes, is just putting together these notepads that have the examples that I sort of hack through the TensorCode documentation and get it to do things that are pretty similar to what I would actually use it for. So I gave you the pre-processing functions from before. Basically, we're just adding to the list, and this pretty much completes the list. Other than when we get into seeing image neural networks, we get a few extra types of functions for that, but this is pretty much it. We have the missing median like we had before, the text dummy, which we had before. I do give you a couple of additional ones that you can use. Encode numeric range, all that does, it's like a z-score, except that it puts it into almost a percent range. So you can, and I'll show you an example of that. It's if you make the range 0 and 1, you effectively turn everything into a percent. So it's just another way of doing that. Removing outliers is a new one. That can be, didn't mean to do that. Removing the outliers can be quite useful because the outliers will really mess up your objective function. So I give you a function there. I'll show you how it's actually implemented. It's relatively simple, but it basically, you tell it how many standard deviations. So you can say plus or minus 2 standard deviations, remove everything that is out of that range. Because the problem with outliers is if you're calculating home prices and the data have a problem where one of the house prices, is 10 million, and it's in a neighborhood where that simply can't exist, the data is just wrong, that outlier can potentially mess up your objective function. So even though the neural network is learning on the other ones, you're going to get a really bad score because it's failing so severely on that one outlier. So removing the outliers is another one that I think is useful. You can remove them. It lets you specify a column, so you can remove them on the input as well as on the output. And then what I want to show you is just how you deal with some other types of data that one student had asked me about was addresses. I deal with addresses all the time because we deal with insurance policies for actual individuals, so we know their address. We know, but how do you take that address and put it into the input into a neural network? That can be kind of tricky because you could break off the zip code, but then there's a bunch of zip codes in the United States. If you do a dummy encoding on that, you're going to end up with thousands of columns. And then the street address and other things. So we end up using latitudes and longitudes and distances between things is a very common way to represent addresses. And I'll show you some of the functions that you can use to do that. And then also time series. So if you're trying to predict something over time, how do you encode it to go into a traditional neural network? And then later we'll see how you predict over time using a LSTM network. So this is the complete set of these. And one thing I will mention that I noticed really just today, first with a question that somebody was asking me that I was responding to an email in lunch around lunchtime, and then another student that was asking me just now. One thing to look at, and as far as the homework assignment 2, if you look on Blackboard under the class discussion, usually if I answer a question for somebody in email and I give them a hint of some sort, I usually go and post it, or I don't usually, I always go and post it into the class discussion. So if you go under the class discussion for homework assignment 2, you'll see that I posted a few pieces of information that I've given out over the last, really over just the weekend. But one of them, and I don't know exactly why this is, I wouldn't have expected this to be the case, but I found that, as we discussed briefly, I know from a few questions, I did extend the 2xy function from the very, very early version that I had on the class website, and also the homework assignment. So the homework assignment, if you're using my template, and you're using the 2xy that I gave you the homework unfortunately has the earlier version of it. I found that in the 2 questions that I answered, an index out of range error went away by using the new one. I don't presently know why that is. The addition that I made down here was really just to make it compatible with future versions of TensorFlow. I didn't think that it actually changed anything. So that might get rid of your out of bounds error. So I do need to look at that one. If I gave you the wrong version of it and you're getting an out of bounds error, then I probably won't be taking any points off for that one, if that was my fault. So I need to look at that one closer because use this one. I think it'll get rid of your out of bounds error. I don't know exactly why that is. In my solution file, I used the old one. It worked fine for me. I think this one's a little more forgiving of index ranges, if I had to make a guess. But I will figure out what that is because Edwin was asking me about it before class, and it seemed to fix his out of bounds error too. So but we'll talk more about that when we get to the end, and I'll review those. Okay, this is a function that I'm giving you that I use this on data sets when I first look at them. It can be very useful. It basically, okay, before I get into that, My apologies. I did want to show you one. Just so that I'm not just giving you all of these functions, I do want to show you how the remove outliers. So the remove outliers function, what it does is you call it very similar to the missing median one, but what you basically do is you call it remove outliers. You pass in the data frame, you pass in the name of the column that you want to strip some outliers from, and I'll show you an actual call of it in a second, but this is more how it works. And then you pass in the number of standard deviations. So you've got that nice bell curve. Well, your outliers are off in the tails. So you pick where you want to slice it. Usually you'll pick 2 standard deviations, maybe 3. Anything that's 4 or 5, 6 standard deviations away from that mean, that is definitely an outlier, and they're very rare. But you can remove them. This does use some pandas code to do it. So what I need to do is basically get a mask. So masks in Python are just a vector that has true or false. True means include, false means don't include, that is the same length as your data set. And what I'm doing is basically taking the absolute value, because you want to go either way, minus the mean. So I get the mean of that entire column here, and I subtract it from the from each value. So this is a vector operation. It's essentially a loop because it's vector algebra. It's going across all of these. It's subtracting each one from that, and then checking to see if it's equal to, or if it's greater than or equal to the standard deviation times the number of standard deviations you want times the actual standard deviation. So anything that is above that, so is out in the tails of the distribution, it's going to remove. So that builds up that map, and then drop, just like you drop the name column or any sort of other thing. When you drop the name column, like you do on the miles per gallon data set, you basically, you usually pass in a 1. Since we're passing in a 0 for axis this time, we're dropping rows. If you pass in a 1, you're dropping columns. And then in code, so that's how that one works. We'll see an example of that. And then this one, encode numeric range. This is just another way of doing it. If you don't want to use the z-score, so the z-score, the problem with it is you basically have, you don't know the range of it. A z-score, it's 0 at the middle, but it's not within some specific range. If you need something between 0 and 10 or 0 and 100, like a percent, you can use the numeric range. And I'll show you basically what it's doing there is it's a lot like the z-score, except it is it's basically forcing it into a range. It's a lot like a percent. You specify the low and the high if you want it to be a percent. The data low, the data high, that's the actual low and high from your column that you're trying to change. So it scales it. You need to know the high, you need to know the low. It basically takes the high and low, so that tells it the range. So that's how big your data set is, and it divides it kind of like you do in a percent, and you force it to be in a specific range. That can be useful for certain. If you have a whole lot of outliers, you can very much force that to be in a 0 to 1 or a negative 1 to 1. I don't use this one a lot. I tend to use the z-score one more. Let's see. Yeah, the z-score there. Okay. Let me skip analyze for just a second and show you the example so you can see what I was looking at there. So you can put the z-scores into there just like we've done, but now you can put the numeric range in there if you want to encode it in this particular way. So cylinders and displacement, basically I am encoding them now as a numeric range 0 to 1. These two columns, normally you probably would just encode them as z-scores. That's perfectly good, but this just shows you what they look like because they're relatively small values. So cylinders and displacement, if you look at what the output looks like now, cylinders, basically anything that is 1.0, since we moved it to percent range, would be the maximum, would be the 8-cylinder cars. So the maximum size. Anything that would be 0 would be, I think there's maybe one car that's a 1-cylinder or a 2-cylinder or something like that. We don't see the entire data set because it's too long. But basically it takes it to a range that is guaranteed to be between 0 and 1. Z-scores, you can't guarantee it. It's going to be between approximately -2 and +2, but if you have some outliers in there, they could go further. There are certain activation functions, and we'll see more of that when we get into architecting the neural network. We have one class specifically on that. You have to guarantee that it's between a specific range, and that is basically how you would do it. Outliers. Let's see, I think the outlier output is near the top. This is important. I tend to do this a lot. So notice I say length of miles per gallon, outliers dropped. Before the outliers dropped is the 398. That's the size of the data set. When I drop the outliers, it's 388. So as you can see, I'm removing any outliers that are above plus or minus 3 standard deviations. If I make that, 2. If I make that 3 and I run it, you'll see that basically, I forgot to run my functions up here so they're available. So now if I run this one, you'll notice more of the data set, the entire data set was included. So there's no true outliers on the miles per gallon. If you remove anything above plus or minus 3, you are going to remove some, but everything is within plus or minus 3 standard deviations because these two match. If you wanted to make that really extreme, you wouldn't do that, but if you wanted to remove anything that was outside of even 1 standard deviation of your curve, then you would get even more removed. So if you look at the standard deviation on, or the standard distribution, normal distribution, hopefully this has it. So a data set that is normally distributed, minus 1 standard deviation, 1 standard deviation, that's, okay, now it expands for me. The internet's a little slow. So when I said basically plus or minus 1, just showing you that it ripped more of it off, you wouldn't want to do that because these are not outliers typically. They're part of your data set. But just for effect, you can remove them to see that it's actually doing its job. If you do 2 minus 2 up to +2 standard deviations, those might not actually be outliers. That's still close enough. I have seen some recommendations to cut the outliers at that. Again, it has to do with what is giving you the best performance. I usually use 3 for data sets that I really truly do have outliers for. because these tails can be extremely long. They can go off to 6, 7, whatever, usually not beyond that. But if you have a lot of, I mean, if you have true extreme outliers, anything above plus or minus 3, it can be very useful to remove from the data set. So that's a very, very common technique. And then I'll also show you the analyze. I find this to be a useful function to use when I first look at a data set. Let me show you what the output is before I show you how it actually works. It's a relatively simple Python or Panda script, but if you run it on the auto miles per gallon, what it tells you is it says it analyzes 398 rows. So it tells you the size of the data set initially. And it goes through the columns one by one, and it gives you the basic statistics on these. And that lets you know if you're going to represent them as categorical, as strings, or as other things. So what it shows you is on the miles per gallon, there are 129 unique values. And that can be important to know. If you have 100% unique values, you probably have a primary key. You probably have an ID field, and you should probably remove it because it's not necessarily going to tell you all that much. But since there's only 32% unique values in there, that's a reasonable one to use. Cylinders is tricky because cylinders, that could be numeric, because fundamentally it is numeric 1 through 8 or more. But this shows you the breakdown of that. So 4 cylinders is 51% of the data set. 8 is 25%. 6 is 21%, and then these others are much smaller values. What you will do sometimes with dummy variables is, like I said, with dummy variables you can end up with a whole lot of individual values. If you have dummy variables that have a relatively small amount, sometimes you can focus the dummy variables just on the ones that have the greatest percentage. So if you need to prune, say you have all 50 states, you want a dummy variable for each state. Certain states may not be all that predictive. Even better than looking at the percentages, we'll see later in this class you can evaluate the importance of each column. And if one column, I don't know, maybe Missouri is not all that important of a state to predict, you can still predict the people who have the addresses. You're just not bothering to encode that particular state for that particular person. So all the other dummies would be 0. You'd end up with all zeros. So that's useful to look at, to know your percentage, to know how those are being distributed. For things like displacement, it does the same sort of thing. It tells you that, okay, there's not all that many displacements, but there's still pretty many of them. The most common displacement is 97. But that's only 5% of the data set. So when you see something like that, you do want to treat that as a continuous variable, as a numeric, especially since these are all numerics. And then the horsepower, again, same sort of thing. 150 horsepower is the most common of the cars because you have 5.53. And then the next one is 90. But again, since there's so many of them, you would not probably want to treat that as a categorical. So cylinders, you probably would, if I was encoding this, I would look at possibly using a dummy variable because there's just so few discrete values, even though it is numeric. Weight, it doesn't even bother to print them out because weight, there's so many different weights. 88% of those are unique So the weights vary a whole lot more than the displacements. Same thing for acceleration. Years, since there's so few years, year, I would really be tempted to treat that as a dummy variable, because the number of the year doesn't necessarily mean all that much. Maybe cars are getting a little more efficient each year, but you don't necessarily know for sure. Same thing for origin. There's only 3 distinct unique values. So anyway, that is just showing you some more of the steps that you two tend to go to, just to look quickly at if you are how you want to pre-process those particular data. Okay, and we saw the pre-processing example. Okay, I want to show you how, because usually when you get data, the data are not as nicely packed as you'll see in the miles per gallon or the irises. Usually you get all kinds of things. Data that I will typically see, if they're, say, medical records, for example, I'll maybe have one row for the person that'll tell me their blood pressure and some basic statistics, but then I've got other columns that are occurring over time. And you get into time series encoding. People have addresses. Those can be very important to encode. Often what you need to do is think about how you can take these individual pieces of data and represent them in a way that they can go into that feature vector, those nice columns that you have in your X, your predictors, so that they can go into a machine learning model so that predictions can actually be made of those. Addresses, I'll do those because if you deal with marketing data, or data that is specific to individuals or regions, you end up dealing with addresses. You end up dealing with another very large block of information. We deal with it all the time in my day job, is census tract information. So every 10 years they take the census. In addition to zip codes, the country is also divided into census tracts, census blocks, all those kind of things. It's just different ways to slice and dice particular data. So what I'm going to show you how to do is, one way that you can deal with addresses is you often will deal with them relative to other addresses. So maybe you're a distribution company and you're trying to predict which of your customers are the most valuable. You have their address. You might want to look at how close a customer is to one of your distribution centers. Or if you think dealing with rural or non-rural customers, you might want to look at how close they are to a city center. So you can get the address of the city center, or the latitude and longitude of it. You can get the latitude and longitude of the actual person, and you usually calculate distances. And I show you how to calculate. If you have a latitude and a longitude, it's very easy to calculate the distance to another latitude and longitude. You basically just you estimate it. You do it just direct, the great arc sort of calculation. You assume the Earth is a perfect sphere, which it's not, but it's pretty darn close. So that works relatively well. Now to look up an address and get its latitude and longitude, that is basically done. Usually, I do it in my day job using a database that we purchased that has this information in it. So it literally, you can buy databases that literally have every address in the entire country and a latitude and longitude. If you don't have that, and you have a relatively smaller number of addresses to deal with, there are APIs that you can use that are really very easy to make use of. You'll notice here I have Washington University's mailing address over at Brookings Hall, And all I do is I use the Python requests. Python requests is really handy for web scraping. So you can send a GET or a POST request off to a website, and you will get you'll get the response back from them. Here I'm calling Google APIs for the geocodes. People who do the geocoding where, I don't know, you bury the caches out in parks and stuff like that. I guess probably Pokemon Go makes a lot of use of this as well. But all you have to do is concatenate the address onto the end of it, and you end up with some JSON code. I don't know if you've ever dealt with JSON before, but JSON, it's a lot like XML. It's just a standard encoding. And you can basically query it. It gives you a JSON payload back in results, geometry, and location. So it gives you, and if you run this, it takes it a moment because it has to reach out to another website. So this is a problem with this particular approach, which we were discussing just before class, that if you have 1,000 of these or 10,000 of these, the one-by-one website might not work as well. There are ways that you can do this at batch. Microsoft Bing, Azure Web Services, they do have one there that's really good for addresses. You deal with this a lot with normal individuals' addresses, not so much businesses, but even if they have moved in the last few years, it'll get you the updated address. But those cost money. I think it's only about $1 or $2 per 1,000 addresses. Yes, you can spin up multi-threads and be hitting them with, but yeah. So this is meant for example for one request at a time. If you need to go into industrial strength where you're most likely where you have an employer paying for this, I believe it's in Azure, and I believe it is Internet is particularly slow tonight for some reason. But there's a database. Microsoft has it available. You can basically buy blocks of it, and the big database that you use for address resolution is something called Melissa. I called it Cassandra. Melissa. Yeah. They probably do store it in Cassandra. Cassandra is the database that I was thinking of, but yeah, there's a whole marketplace of this type of data that you can acquire and use for various purposes. Even web searches. There was a different company that I used to work for quite a while back. They were doing search engine optimization, so SEO, where basically they want to try to make Google send them as much traffic as possible. Now, Google has done several updates where this does not work very well, but 10 years ago when I was doing this for the particular company that I was with at the time, which I won't mention, what they were doing is they were looking at all their competitors' sites, and there's a way you can query Google, and basically it'll tell you all of the sites that link to a particular site. So they were building up profiles of what the most valuable links were for search engine optimization, and that gave them very useful information until Google got mad about too many search requests per second coming from a particular. Wikipedia will shut you down too on this. And by the way, if you ever want to do analysis on Wikipedia, you can just download the whole thing. You can download the entire Wikipedia as one giant XML file. Or I would, kind of like in the first homework assignment where we calculated the efficiency column for the cars, I would just add a latitude and longitude using that exact same method, because in Pandas you can add columns quite easily. But yeah, this is the way you do it in an example. If you're doing it the way we do it is basically we have a large database that has, like I said, all of the addresses. But what you have to deal with is people tend to write their addresses differently. So one Brookings DR, they might do DR period, they might do DR IVE. St. Louis is a mess. I mean, SAINT Louis, ST period Louis, all of that. That's what the Melissa format does, is the US Postal Service has a standard form of how you write an address. And there's really, you can vary it, and their machines are easy enough to figure it out. But if you normalize an address, there's only one form. There's only one way to actually write it. So you don't have to deal with Avenue completely written out, or AVE, or AV, or however anybody would ever abbreviate these. So if you deal a lot with marketing data, this becomes a specialty unto itself, learning how to deal with all the nuances of addresses. And the way we do it is it's in a big SQL database, so I just literally join to it and can look it up extremely quickly that way. If you're using an external provider like Bing, you will most likely package these up as 1,000 blocks or 10,000 blocks if you're looking it up for a big piece of data, and that will go across the wire as one request, and then all your results come back. But those are paid services. This is good for if you just want to do a few. Oh, and I will show you after we go through the class material, but before we look at the second homework, I did post the information online for the final project. The final project, we'll go through that, but basically I am flexible on that. I've already talked to 2 of you who had specific data sets that you wanted to do something with. If you have a data set that you want to do this type of analysis on, and you want to completely change the parameters of my final assignment, I'm quite flexible on that. Just send me an email. But if you are taking these addresses and you're trying to put them into the feature vector, so the input to the neural network, you might be tempted just to put, the latitude and longitude, these are fundamentally angles from the center of the Earth, essentially. You could literally just put these 2 values right into your data set. That would work better than an address. You always have to think about, though, when you're putting data into the feature vector and you're trying to pre-process this data, what are you really giving the neural network to work with? And in this case, you're giving it, now Alaska and Hawaii are not where they really are, obviously. That's just the way the map is drawn. But this is showing a particular habit, cigarette smoking, so you can see that some states do, in fact, there's almost a tobacco use belt. So I work for a life insurance company. They're always trying to predict these things. Where do people smoke more than others? So I guess we'll go sell in California or something such as that. But the point is to show you that just the latitude and longitude together are predictive in some cases, because you would see that literally right about here would be the cluster, or the center of that, and as you went up or down, it might decrease. And the neural network, with enough hidden layers, it can create several centers, and it could actually learn to predict your probability of being a tobacco user just based on where you're at on the map. It's just a probability. It's not going to tell you literally for sure, but it can be a good input into a much more complex algorithm. We do use this as one of the inputs into something that we look at. It's not a very good, it helps some, it gives you a baseline, but fundamentally, I can't really say a lot about you personally just from the fact that you live in California. It's just a beginning of a probability of that. But usually you want to get more accurate than that. So a way that you might do this is if you had, I don't know, data on 100,000 people throughout the United States, and you knew if you had their address and you had maybe just their tobacco use flag, true or false. What you could do is you could literally get all of the latitudes and longitudes, and the neural network would basically build a map like this of its own. It wouldn't need this map. It would essentially create it because you would have this data already on your people. What you might want to do, though, and you would be more successful, is if you looked at certain centers. So you might pick a couple of points here, and you would engineer several inputs of how far you are from each of the population centers, perhaps in the United States, or how close you are to a city center. The way that I calculate city centers on one model that I did is I took just the top 100 populated cities in the United States, and I got all of their latitudes and longitudes, and then for each person I say, okay, of those 100 cities, those 100 latitude and longitudes, which one are you the closest to? And then what's your distance? And I treat that as your distance to a city center. Now 100 is, I actually needed to do a little bit more. There's sort of a sweet spot where you're not, I mean, if you don't put enough of them in there, St. Louis might not make the cut, and you might be calculating your distance to the city center of Chicago. So these are all things. I can't give you one rule to sort of define it for everything, but if you're looking at address and spatial data, this can be a way to look at it. If you're looking at a different type of data, you have to come up with how do you take these values and turn them into numbers, relations between different things. And this is a very labor-intensive sort of trial and error approach. I tried many representations of the data. Most of them do horribly. A few of them do well, and you build from there. So if you want to calculate the distance between two things, it's pretty easy. I show you how to do it with the great distance. I don't know, I'm pretty good with trigonometry on a flat surface. I do not, and I know most of the distance and whatnot formulas by heart there, but the solid geometry where you're calculating essentially, if you have 2 points on the Earth, P and Q, how do you calculate what the shortest distance is between them? I pretty much just plug in the formula and get the result. So I took the formula that they give you here with the calculation, and you get the final distance. Implementing it is relatively straightforward. The most common mistake that people make when they're implementing this one is basically you have to convert the latitude and longitudes into radians. Because they're a latitude and longitude, fundamentally they're angles to the center of the Earth. So you have to convert those into radians, otherwise you're going to get really bizarre distances that will not make any sense. And then basically that equation that I had up there, I plug it in. And now what I can do is, and I'll show you one other thing. I took that code from up here. Basically this relatively simple looking code, I made it a function. I always like to make helper functions because then I don't have to keep copying and pasting the same code over and over and letting it get completely jumbled up. But this basically, you pass it an address, it gets you the latitude and longitude. It's simply calling the same thing. It does throw an error if it can't find your address. And then basically I put a address between Washington University and school I'm currently attending. So my two graduate degrees, I calculate how far they are from each other, and it's in Fort Lauderdale, Florida. But if you run it, you have address 1, address 2, and usually you want to put the addresses in this form so that Google can find them. Google is pretty tolerant of if you write out drive or do DR, it's basically just doing the Melissa encoding. And you can run it and it prints out the distance. So the distance between St. Louis, Missouri and Fort Lauderdale, Florida is about 1,700 kilometers. That's another thing to be careful of too, is units. I've been messed up by that many times in medical reports. There are so many different units. Are you talking about cubic centimeters? Are you talking about cubic inches? Basically, the approach we follow is most medical records are all metric. I tend to just put everything into metric, convert it. That way I'm not literally like converting one part of empirical to another part of empirical, but if you can, so I know a lot of some of the code that it has to calculate BMIs and other ratios. If you just put everything into similar units, that's usually a good idea. So like I said, distances, if you're dealing with addresses, you might want to think about distance to a major metropolitan area, distance to one of your competitors. If a competitor is closer to the customer than your store, distance to a distribution center, distance to a real retail outlet. This is just a somewhat contrived example, but I basically looked up the mailing addresses to 10 universities and just showed how you would do this in a loop. And I just calculate the distance between each of these, and these are the top 10 US News and World Report. Basically, because I wasn't feeling creative, that was just a nice, easy list to grab. But this does show you some interesting things that I've dealt with in addresses that are like Princeton. The address to Princeton it's Princeton, New Jersey. There is no street address. It's just Princeton University in Princeton, New Jersey. They don't have a street address. And you'll find that with a lot, like the mailing address for the IRS. It's somewhere out in, I think, Utah, Ogden or some city, but there's no street address. MIT or Harvard does not have one. Some of them do. Google is smart enough to figure that out, but what you have to be careful of is if you look up Princeton University, it won't give you this part. It'll just say mailing address, Princeton, New Jersey, that zip code. Because basically that's kind of their own zip code. So they can do that. But what you have to be careful of is sometimes Google will get confused and it'll just give you a city center. It'll end up giving you the center of Princeton, New Jersey, which might not be the coordinate you're looking for. Yeah, I've dealt with addresses for a while and stuff. If there is one particular mistake you can make in addresses, I've made just about each of them, but they can be very interesting. So what I do is I create latitude and longitude 1. I look it up for Washington University. Since Washington University has a street address, I don't have to put Washington University, comma 1 Brookings. I could. Google's smart enough to figure that out. And if you run it, it takes it a moment because each of these is a separate web call. You can always make sure it's running. You see the little asterisk there. And at the end, it will give you each of those. Boy, the internet is really... Except I wouldn't expect the internet to be slow here because when you run this on Data Science Workbench, you're actually using their internet connection to do it. But maybe our internet connection is slow and not receiving the response. All right, well, we will go ahead and we'll take the 10-minute break right now, and then I'll show you the other two examples of other types of data that you might want to encode. All right, we will go ahead and continue. Let me show you these last two things, and then I'm going to take the last part of class, and I want to review a couple of the common areas of confusion for the homework assignment. All right, so the last two are just, again, how do you deal with text values? I show an example. This is from the book as well, but you might have heard of bag of words. It's a way that you take just text strings and you represent them in a way that the neural network can read. Consider if you had these three sentences. All we're doing is you want each of these would be a row in the data set. So these might be titles of a book, and you might be trying to predict if somebody reads this particular book or not, or if they like it or not, or if it's a fiction or nonfiction, whatever you're trying to classify. So what you do is you find the number of discrete words. So how many actual words are in there? If you basically put them into a dictionary or a hash map, how many words are there? And I never did like this term, but when you deal with natural language processing, you'll hear a term called a stop word. I don't tend to like that because I don't think it's that descriptive of it, but a stop word are basically just fluff words that are not that important. Of, and. So here I do actually put it into the list, but if you look at scikit-learn, there are all of the natural language processing. You can tell it to remove the stop words. And is a very common stop word, but here, just for simplicity, I put them all in. So you end up with a dictionary when you use bag of words, and this is all built for you automatically. And then what you do is to encode each of these, so of mice and men, you basically count up. So you look at which index in there these actually had, and I have some extra spaces in this one. And then you expand it. So this is what actually goes into the neural network. So of mice and men, it has and, which is the first one, 0. The second one is blind. Blind doesn't occur anywhere in there. The next one is bluff, doesn't occur. The next one is mans. Men, the fourth one, that does occur. So you're just doing a count, a histogram. You're counting up how many occurrences in your master dictionary occur for each of these. And in scikit-learn, you'll use the count vectorizer. So just to give you a very quick example of what this looks like, it basically, you give it a corpus, which is just a list of the text documents. I usually set the min degrees of freedom to 1. That's essentially a default value. You call fit, and it analyzes this entire thing, and it builds that dictionary. And you'll notice it shrinks these all down. So this is the first document, this is the second document. This list here is all of your unique values, and then the index, 0 means it's the first one. And then so it's just a lookup. And means it's the first one. Document, and it's just the way that this algorithm happened to line these up. So the reason that these were all encoded this way is 0, so there was 0 occurrences of and in the top one, and that's true. One is document. There's one occurrence. And now you have this nice fixed length vector for it. The only trick here is you don't want your dictionary to be too big. That's why you eliminate stop words. And so the trick there is very much, I've used this on Wikipedia where we look at Wikipedia medical conditions and we're doing bag of words on it. The real trick is for that one, for when I was running that particular model, I had 500 inputs. So I was finding the 500 words that classified it the best for what I was looking at. And the way you do that is feature importance. And this is a very useful technique to do. The example that I give you here uses the AutoMPG. I like to reuse the same data sets over and over and over again. Otherwise, I would be spending the next 10 minutes explaining to you a new data set that you hadn't seen before. But remember the name column. We always just took the name column and threw it away. Now we can see, can we actually do something with that name column using bag of words? So what I do is, you'll recognize this code from many, many examples. I am basically just pulling it in, but now I build the corpus, which is your collection. The corpus previously I just hard-coded to these 4 or 5 documents. Now I'm setting the corpus to the name of all the cars. Then I'm going to build the vectorizer, just like before, and I'm going to fit. And I'm going to print out the mapping, and then I'm going to print out what each of these look like encoded. And this ends up being a disaster. You don't want to do it this way, because the name field, even on a small data set like this, we end up with a ton of individual words. So if you look at it, this is what the mapping looks like. We have all kinds of pieces of car name with Zephyr and Cougar, and it's also interesting too, you see this a lot in data sets. They have errors in it. That was probably and it's a name of a car. I was thinking it was T-O-Y-O, yeah, it's spelled wrong, T-O-Y-O-T-A, so that U does not belong in there. But you'll see this very, very commonly. You'll see this because I have run this sort of thing against the entire Wikipedia. You'll see all sorts of spelling errors, common spelling errors show in the tails of it. They're not very common, but so you end up encoded. It can't even show it to you because you would have a column for every single one of these car types. And that would be very obnoxious to deal with. You don't like to have neural networks with tens of thousands of columns in there. So what you can do that is very useful, I use random forest because TensorFlow does not have a real good way of doing this yet. Remember, again, TensorFlow is less than a year old, but with random forest, I can fit a random forest to it, and this shows you how interchangeable this all is. Basically, instead of doing TensorFlow regressor, I just put in random forest regressor, and now the whole thing is running against a random forest instead of a neural network. When we get to ensembling, this is very cool because we can create a bunch of neural networks, a bunch of random forests, a bunch of gradient boosting machines, and just like the individual members of an orchestra, we combine them together and they produce an even higher, more accurate prediction. But I fit it, just like we do with the neural network, the X and Y. Importances, I now obtain the importances, and we haven't really looked at that before. What it does is it basically takes all of the features that were in there. So I created you can see that there was literally, if you look at the number of unique words in there, there was I think it actually stopped at 300. I think there's a few more. It takes all of these various, so I literally created 300 columns wide. That's normally too big, but I tend to just throw everything at it, and then I ask the random forest, because it'll be similar to a neural network, what is the most important ones? And you'll notice that I have no idea why the 99E is particularly important. You don't always know. But it'd be Gran, I'm guessing because that is probably something on a sports car or a big car, like Gran Torino, something like that. The C20, and then Peugeot and Volkswagen. That doesn't surprise me that you start to see names of car brands high in the list. That's just saying that Volkswagen and Peugeot and Beetle. So yeah, Volkswagen's very distinctive. Knowing that it's a Volkswagen, it doesn't necessarily mean bad. It doesn't necessarily mean good. There's other analyses that you would do, but these are the most important words. And what I would tend to do, so you usually do see Skylark, the Lexus, Rabbit. Again, this is a fairly old data set, but you would take maybe the top 30 or so, and you would only put those in the dictionary. If the other ones showed up, you just ignore them. If you were classifying Wikipedia articles, you would have to do this. Otherwise, I don't know how many words, or maybe, actually I think it ends up being around 10,000 when I was pulling most of the major medical conditions. That's too many. You don't want to have that many words. So I was limiting it down to around 500, and I was able to classify. And as you peel into this deeper and deeper, like I was looking at medical conditions that were more life-threatening. And what I found that was interesting is words, and I wasn't using individual words, I was using n-grams, so sequences of words, which is kind of the next step up in complexity of this. I found that the word that popped to the very top of the list, it was very interesting, was survival rate. So if you think about it, every condition, it's almost an actuarial concept, but every condition has a survival rate. Crossing the street has a survival rate because some people don't make it. Very few don't make it. Walking out of a school building has a survival rate, but usually the common cold has a survival rate. Paper cut also does too, but the article in Wikipedia is not going to mention it unless it's huge, or unless it's not huge, but unless it's a factor in that. You're not going to go to the doctor and have him tell you, oh, you have a 99.9% survival rate on your common cold. He would probably just scare you. Wait, survive? So there's a chance I won't? So anyway, that shows how you can analyze these. And then it got quite a bit more complicated in that there were other sequences of words that it was looking for. But bag of words, very common. It's a technique that you use in text mining. Sentiment analysis makes use of this sort of thing, where you're looking at, there's been a lot of that done in the election here lately, just doing sentiment analysis on tweets, and not just the tweets that the politicians are throwing at each other, but people are talking about them as they're debating and as they're doing things. So that's bag of words. And again, if you wanted to make use of this, you would literally just pick however many of these you wanted to. You would use the vector encoder like you had here, but you would limit the dictionary and pass it in as a parameter to the vector encoder, and you would not get this punishingly large set. So anyway, I tried to just pick some of the more common. I mean, I could make this endless in terms of how you represent different types of data in this format, but since you're dealing with me, these are the common encodings that I've used for various data sets that I've worked with. And then the final one, I choose this one because it's very interesting, because there's a lot of interest in this. This is how you predict time series. Time series is huge. It's not just finance, trying to predict if a stock is going up or down. It's speech recognition. Because speech recognition is basically the audio wave going over time. It is all kinds of things. The self-driving car, as it's driving down the street, is very much time series. Things are happening in a specific order. We're going to see here how you encode a time series for traditional neural networks and also support vector machines and all these other models. This is one of the key advantages of neural networks. In a lot of classification problems and regression problems, they perform not much better than a support vector machine or a gradient boosted machine or a random forest. This is where they really shine, because for all the model types, except for neural networks, you have to encode that time series in this way or a similar way. But with recurrent neural networks, the LSTMs, which are one of the most current areas of deep learning, which we will get to in a few weeks, you don't have to go through this. So basically, if you look at, you're trying to predict a stock. It's at $45 today. What will it be at tomorrow? You have to look at what that feature vector is going to look like going into the neural network. You can't just give it 45. Because, okay, the stock was at 45. Historically, it's probably been at 45 a bunch of times. That one value, that one point in time, if you just put one input neuron where you had 45, your training data would be very inconsistent, because your training data might say, okay, 45, but then the next day it was 46. Then you might have another case where it was 45, but the next day it was 40. It's just not enough data to make an accurate prediction. Trends are what they tend to analyze for this. So it was 45, it was 47, 48, and then, oh look, that trend caused it to drop to 40. Now you would look at much more complex data than this, but this is just a simple time series. The first step is you want to normalize the data. So you want to look at how much it changed, what percentage. So day one, it changed just by that amount. Day two, it did not change by, let's see, how am I encoding this? This is, I think these are percents. And then it goes, basically, we're removing the magnitude of it. So you don't care if the stock is up here bumping around or down here moving around. You just care about the degree to which it's moving. Yeah, it's looking at the percent move from the previous day. So basically, now you can take these in sequence. So maybe you have 3 input neurons. It moved by that percent, then that percent, and then down by that percent. So these 3 together caused it to then the next day move by 2%. Now you've got more data, so your neural network has more to lock onto. If you're using anything but a deep neural network, this is how you have to do it. This is the only way you can do it. And there's other ways to do it. There's all sorts of financial ratios that they use. But fundamentally, you have to encode the sequence some way. Recurrent neural networks, and I won't get too much into that yet because we have a whole class on that, the neural network retains short-term memory. That's what LSTM means, long short-term memory. So it remembers this, and you don't have to tell it, we're looking at sequences of 3. It might deal with a sequence of 12 if that's the pattern. Or it might deal with a sequence of 2 if that's the pattern. So That's a really advanced feature of deep neural networks, and that's why deep neural networks are so good for like Siri and speech recognition and even financial applications of these. You could do an entire course on time series. I've seen it done. It's because then you get into all the financial and signal processing. So I give you a very simple little Python script that I wrote here. I am basically just normalizing them. All I'm doing is I'm keeping track of the last price. Initially it's none because I'm at the beginning. I'm keeping a list, the result that I'm going to return, and I'm just going to loop over all the prices in history. So you pass in history, that's just a sequence of prices. I'm going to loop over it. If I do have a last, so I do have a previous one, I won't have one at the very beginning. I just append price minus last divided by last. And the only reason I put these in, I put the float in there is just in case they come in as integers. If these are integers, then you're going to get an integer division, and most likely it will go to 0 if it's a fraction like that. So the float just converts one of these to floating point. And then I set last equal to the price, so I just keep moving forward, and basically when you run that, it will give you all of the prices just normalized by percent change. This function is from the book. It's a little more complicated. It does this. So it finds, okay, 0, 0.2. It takes that normalized sequence of numbers and it breaks it up into, these are called time windows. So you have a window size of 3 to predict another. So it's going to return the x and y. So this is very much like an encode xy or 2xy like we have. You could feed it right into a neural network. I basically count out how many rows I'm going to have. I have a lag size and a lead size. Lag size is this. So these 3 lagging numbers indicate a lead of this. So this is a lag size of 3, lead of 1. Because you might want to predict further into the future than just 1. I count the output rows because we're going to have a number of output rows. We're not going to have an output row for every single input number in the sequence because you need enough of them to build the window. So they have to build into the window. So you're going to have fewer. And it's basically going to be the total size minus the size of your lag and your lead plus 1. So lag size plus lead size, that's the total size of a row, plus 1. That just accounts for the final sort of round. And that lets you know how many you're going to actually have. So we loop up to that row count. We encode the x, we encode the y. They're both pretty much the same. All I'm doing is looping across according to the lag size, building up the lag window from the source. Then I build the lead, put it into y. Lag goes into x, lead goes into y. And now I have a program that basically I can give it those same numbers that I did manually, normalize them, print out what they are normalized, and then convert it to the time window. So that's the output. That's the normalized price history. I can round it. And then I can call the time box with a lag size of 3, a lead size of 1. A very good practice sort of example for this is you just do the sine wave and you see if the neural network can predict the sine wave. It learns the sine wave pretty easily. If you tried to have the neural network just predict sine with just the x to predict the y, that's not quite enough information. It needs the full trend. So anyway, these are 3 different types. We'll do a lot more with time series because it's a very important concept in deep learning. We have a whole class session just on that. If you have any interest in either speech recognition or, I don't know, get rich making the neural network predict the stock market for you, that is that's a very can be a very interesting topic. We tend to look at time series, just looking at people's blood pressure over time, other vital medical statistics. What does that indicate of their overall health? And it's just, how do you get this data into that feature vector? All right, I want to show you one more thing. Just the it's not due till the very end of class, but I put it there in case you want to be thinking of it ahead of time. But the final project wait, don't need to go there. So yeah, the midterm, we discussed that. The midterm is due in a couple of weeks. I'll probably send out the reminder. The midterm is less technical than the programming assignments, so try to give you a little of both. But the final project is basically what I give you is, this is very flexible. If you don't have a particular data set or experiment that you're wanting to run with deep learning, that's perfectly fine. Then you can basically just follow exactly what I have here. I give you a whole bunch of data sets that you can choose. If you click the link on them, it will take you, okay, GitHub is not exposing my link, but if you download the PDF, it'll take you to a link. If you need to look at any of them, you can almost just, they're all from UCI. So you can just do abalone, dataset, UCI, and it'll take it. So you get all the information there. I chose these data sets because they're really not that bad. If you want to, if you're brave, you can certainly just pick any data set that you want to from UCI. The risk there is not all of these data sets are particularly conducive to deep neural networks. Some of them are, they're just in a different format than you would need to, so you would have a lot of pre-processing. So if you're going to choose a data set other than the ones that I gave you, I would just suggest sending me an email. And if you are choosing something that is really, really difficult, I will tell you, and I will tell you how I would encode it, but you might then, you don't have to choose that one, but you can ask me. But these are a number of data sets. They're somewhat interesting. Some of them are just looking at liver disorders. So there's a couple of biological ones. Credit approval based on other rates, horses and colic, hepatitis, a lot of health ones. Wine quality. You pick one of these, you basically create I don't even necessarily make you do, I tell you the criteria here. Just use a training and a validation set. You can use K-fold if you want to. It's up to you. Train it, so the whole idea here is just to get you to use a data set, produce something like the homework assignments that we've had with Iris and MPG, to get a new data set, to think about a new data set, to think about how you might encode it and present it. Most likely you're going to use all dummy variables and z-scores, but that will be up to you. And then use an evaluation metric for your network, and use a graphic, like either a lift curve or a lift curve or a confusion matrix. Okay, so that's that. That's not due for quite some time, but I'm trying to put these all out. This is the first semester I've taught these classes, so the reason homeworks 3 and 4 are not out there yet is because they literally do not exist yet. So 3 I'm putting together. 3 will be the one where you will submit it rather than Blackboard. You'll submit it to Kaggle. So I've created a little Kaggle competition site. So you'll see how to actually submit it to that. It'll end up actually being easier than Homeworks 1 and 2 because you'll just have one data set to fit. Your score won't matter as much because you'll basically just put it in a Kaggle. You guys will all be ranked from the most accurate one to the least accurate one, but that's not what your grade is about. Your grade is just about, can you produce the output file to send to Kaggle? And then your name on there, I'll encourage you to choose a alias since it is public to everybody. You can put your real name in there or you can create an alias, totally up to you. But what you'll submit in Blackboard is your alias name so I can line it up to you. So anyway, that's coming. I'll probably have the information on that when you return because we don't have class for 2 weeks due to fall break and due to me being at a conference. I will give you the PDF from the conference because it's very much about this sort of stuff. All right, what I'm going to do now is basically, I've had a number of questions about homework 2, and they seem to fall into several categories that are fairly similar. So if you're done with homework 2, you've submitted it, you are happy with it, you don't need to stay for the rest of the class. I basically have everything. That's everything that I have. But if you would like some additional information, or you would like me to look at something related to your homework 2, basically what we're going to talk about, one is the difference between classification and regression and how you measure the two. And then just a few common things that I've seen people asking me about. I'm pretty sure that... Yeah, so the reason we're doing that is, let me get the assignment up because then I can illustrate it better. The reason there is to give you sort of a real world example of what you'll do. So when you're what happens is when you create a data, so when I create a data set for real, I'm given a bunch of historical information on some process that the company wants to automate. So maybe I work for a credit card company and I have all this credit information for individuals, and I'm supposed to predict if we would give them a credit card or not. What I do then is, that's very much just like all the homework assignments. You have this nice big data set, you calculate the mean, the standard deviation, so now you can calculate a z-score. So you want to get, well, you need it for each column. So you'll have a mean and a standard deviation for each column. The reason you need to do that is, say you've created your neural network on 100,000 rows of sample data that they've given you, but now you need to roll this thing into production, and maybe every minute or two, 3 credit card applicants come in. You need to send those off to the neural network. You need to use the mean and standard deviation that you did on your training set. Calculating a mean and a standard deviation on that small of a data set would be meaningless. So that's each of these questions is meant to be some aspect of real world usage of these, but that's what this one is for. This is just, you've created your neural network by analyzing the last 10 years of stock market data, but now you want to predict tomorrow, and tomorrow has just come in, so that's... Yeah, good, very good question. Very good question. All right. One, and let me go back to, because this was a common question that some of you asked me. If I go all the way back to class 2. So classification and regression, it's very, very important to know the difference between those two. And if you look at the homework assignment that I gave you, basically, Question 4, 4 and 5, I tell you literally use classification or use regression. So this one I tell you, usually the iris CSV is used to classify a species. This time I flip it around and just make you turn it into a regression problem. So you're trying to predict one of those 4 measurements. The big difference between classification and regression is classification, the answer is not a number. The classification is, a classification neural network will tell you, like an iris, which of the 3 irises is it? Regression is a number. So think about the question 5, and this is a little bit confusing, but question 5, I'm telling you, normally you regress, so regression, to find the MPG. Not this time. Use the other fields, including MPG, to predict how many cylinders the car has. Treat this as a classification problem. So this is a good illustration of it. If you're trying to predict how many cylinders a car has using regression, you could do this either regression or classification. And so long as your code comes close to calculating something, if you ignored my advice and made it a regression problem, you'll probably be fine so long as that works. But the difference here is, if you're treating this as a classification problem, your output from the neural network is going to be something like 2, 4, 6, 8. Don't even think of those as numbers. That's classification. So it's very important, and there's a question on the midterm that sort of has you explain this, of how do you measure the accuracy of this? This is like your multiple choice exam. If I handed all out Scantrons and you chose A, B, C, D, the way you rate this is accuracy. So for each of those 398 rows, how many times did it pick 4 when it really was 4? And how many times did it pick 8 when it really was 8? There are no partial credit for, say the answer was 8, it really was 8, and you chose 6. You might say, well, that's closer than saying 2, but not in accuracy. Accuracy is just like the score on a test exam. 80% means you picked 80% of these correct. There's no partial credit in classification. Regression, on the other hand, and you could treat this, and the question I was suggesting using classification, regression is numeric. So it's almost like a formula. You put all this stuff into the formula and it gives you a number out. This, you're going to get a number between, I don't know, 0 and 10, I would hope. I would hope it wouldn't go too far outside the range of what the real data was, but if the neural network wasn't trained well. So when the neural network is predicting with regression, you get an entirely different type of answer. You can get the car, it might tell you that the car has 7.7 liters. It doesn't know. There's no car that has 7.7 liters. I mean 7.7 liters, yes. 7.7 cylinders, that would mean, I guess it has 7 normal-sized cylinders and an 8th one that is smaller than the others. But that's meaningless. It doesn't. So that's how a regression problem would solve this. Regression, you evaluate them completely different. This, you evaluate accuracy. This, you evaluate RMSE. So how far off was it? The neural network predicted 7.7, it was really 8, so it was 0.3 off, so you sum up all those differences. So I think there's a question on the midterm that asked that. So when I asked you, basically, are you using accuracy or RMSE, If the output is a discrete class like that, like an iris species or a number of cylinders, then you would want to use accuracy. Otherwise, you'd want to use RMSE for regression. So, and there are other types other than class. There's clustering and others, but these are the only two we're dealing with in this class. Those are the two most common of supervised learning. So, where this becomes very important is if I go into Data Science Workbench, and I'll show you, maybe I'll go into GitHub. Yeah, the internet is absolutely dragging tonight. So if we look at class 2, so of the data sets, except for homework 2, where I flip it around for question 4 and 5, IRIS is your classic classification, MPG is your classic regression. So if we look at down here how we if we look at the code for IRIS, basically the really important part, and several questions that I answered in email from several students had this incorrect. So this is really important for classification and regression. Notice that it says TensorFlow DNN classifier. That means you are using a classification neural network. If I made this TensorFlow regressor and I tried to do IRIS, it wouldn't work, because that's how you tell it if you're doing classification or regression. So whenever you're doing classification, you will always see this n classes equals something. So for the miles per gallon one, you would want to see how many different types of engine configuration there are, and I don't remember how many it was offhand, but say there was just the 2468 or the 3468, it would be 4. If you're doing regression, then you shouldn't have that n classes. If you see regressor and you have n classes here, remove the n classes if you're doing regression. It'll take it, but it'll just kind of do the wrong thing in TensorFlow. So this is a good example in class 2 of how to do it. I show you just the basic classification case, which is this. If we scroll down and we look at MPG, which happens next, you'll see how that call changes. So miles per gallon, you'll notice now I have TensorFlow regressor, because miles per gallon is a regression. And you'll notice that I do not have the n equals 3 on there. Because there's no, it's predicting a number. It's predicting miles per gallon. I don't know how many miles per gallon there are. Another common question that I would get is, the accuracy was not as great as mine was in the sample output. Usually that's because I have more steps. So the approach that I use is usually I put a higher step number. Now this example here does not, I hadn't shown you early stopping yet because this is class 2. Once we get early stopping, you can make steps 1,000,000. It doesn't matter. That's just a maximum ceiling. The early stop will stop you once training is no longer helping. So number of steps when you use early stop doesn't matter nearly as much. That's just the upper limit on it. To grading, I mean, I'll be completely straightforward with you on that. I tend to give a lot of opinions in terms of I'll mark this and I'll say I don't like that and I'll say I don't like that, and then I'll take a half of a point or a full point or something. I want to give a lot of feedback but not impale you in the process. So that's usually how I go through these. So I spent a couple of hours, I think, going through the first one. Usually I load them all. Another thing that I do too is I use Jupyter Notebook for educational classes, and it's very popular for that. I use an actual IDE when I do these because then I can debug it. I can stop it at a certain point. And that's definitely an option. The reason I didn't use that is that introduces a whole nother level of complexity because now I've got to show you a particular IDE and you've got to get TensorFlow installed and running on your local computer. But that is an option too for these. Let me go to
maybe out somewhere else.
it's back one. So this is my solution to it. Now I programmed the solutions to the, like I said, this is the first time I've taught this particular class, and I created the solutions to the homework assignments way back in August. So basically, so I would know what to cover to do it. My solution here, I will be updating it before I send it to you because I don't actually have the 2xy function. I was originally just hand coding it in each function. So just be aware of that. That's a little potentially misleading if you look at this version of my solution. But these last two, what is very important to do is you definitely want to have the encoding of the z-scores and the dummy. This is 4. You definitely want to have that part there so that you're doing the x and y train with the x and y train there. So train, test, test, like that. But this is what I was getting to before. This first one, even though it's the iris now, just to make it interesting, I make you regress on one of the inputs to the iris. I'm using a regressor. And notice since I have a regressor, I don't have a n classes. If you see regressor and you see n classes, get rid of it because the n classes, make sure you really want to be doing regression. And if you really want to be doing regression, then get rid of your n classes because it's meaningless to a regression one. And unfortunately, TensorFlow, I don't even know what TensorFlow is doing when you do an n classes on a regression. I'm suspecting it's doing a multiple regression where it's actually regressing on several values, but I'm not totally sure. But it's an autocorrect situation. Same thing on the early stop. You don't want to have n classes. You want to fit it. And then the other important thing, on a regression problem, notice I'm evaluating it with RMSE. You always want to use RMSE. There's a ton of these, but for this class, always use RMSE when you're doing regression. Always use accuracy. So when you pick one of those data sets for your final exam or your final project, first just decide, is this classification or is this regression? And that's mostly up to you because it's your own project at that point, but what do you want to get from it? If you pick regression, then you want to be using a lift chart for your chart and you want to be using RMSE for your evaluation. Notice on 5 where I request classification. So classification, you'll notice I'm using a TensorFlow DNN classifier. I'm doing n classes equals num classes. That's because I'm incredibly lazy and I didn't want to go to Excel and count how many different engine configurations there are. So what I did, you don't have to do it this way, but you certainly can, is I basically get the length is when you have the encode dummies, and again, this is something that I'll be updating in the solution before I send it to you. I will use encode dummies. This is basically encode dummies. I just pre-packaged them all to make them easier. I'm basically asking it, how many different cylinder types did you found, and that becomes my number of classes. I tend to do this because I've been burned by that before, where I create a classification network. And then in academic projects, your data set doesn't ever change. It's just downloaded from UCI, and that's all it is. That's all it ever will be. But when you're doing real-world data science projects, you'll all the time hear from, it's just this mad rush of all different parts of the company bringing data together, and then all of a sudden, invariably, as soon as I have my model halfway working, one group says, yeah, my part's not right. Here's the new data set. And what used to be 4 classes, maybe now is 8. So that's why I do stuff like that. But if you want to just count them, that's fine. So the thing to note there is I have the classifier, I have the n classes. Very, very important. If I didn't put the n classes here, I think it would actually error out. I don't think it would even generate something. Steps, 500, that's a little lean, especially since I have an early stop. This is just me copying and pasting it, and it worked well enough. What I copied it from had 500. I was happy with my score. You could make that 50,000. The early stopper is still going to hit it. And then you'll notice at the end, I'm not using RMSE. I'm using accuracy. So always evaluate a classification problem with accuracy. Or ROC. I introduced ROC mainly for completeness. You can use ROC on your final project if you want to, but I don't tend to use that one a lot. There's a lot of people that really like it. It's a personal preference. I don't do a lot of binary classification, so that's probably why I don't use it as much. So that is basically just an overview of those. The homework, I'll update my solution file. I will also point out on yours specifically where you varied from mine. I realize 3 and 4, or 4 and 5 gave people the most amount of trouble on this one, so I will be aware of that as I grade those two. So submit what you have. I will, even if it's not working completely perfectly, the worst thing you can do is submit nothing. Then I have nothing to give you partial, because partial of 0 is 0. So send those to me sometime tonight. The Blackboard deadline is, I don't think Blackboard actually stops you on that, but I mean, I will grade that probably Thursday, so that's when I'll go through all of these and you'll get your answers back. If there's any specific questions on these that you want to ask before the class, that's fine, or if you want me to look at something after class, that is also fine. So that is all I have for this week. when we get back, I will give you the information on. The midterm is due by then. If you have any questions on the midterm, definitely send me email. I usually answer those pretty quickly, unless you catch me on a bad day, then I get to you the next day. But I try to always answer those within a day.